currently in operation. He also co-founded the CERN RD53 collaboration, which aims to deliver the pixel readout integrated circuits, the most complex chips developed for particle physics to date, for the coming upgrades of both the ATLAS and CMS experiments at the Large Hadron Collider, LHC. At the low energy intensity extreme, Dr. Garcia-Severez focuses on technology to extend sensitivity of low mass particle dark matter searches and is a member of the Tesseract collaboration. Since its inception in 2018, Dr. Garcia-Severez has led a collaboration of 7 institutions under the Quantized Initiative, Quantum Information Science-Enabled Discovery, which aims to develop new types of low-energy, noiseless phonon sensors by leveraging advances in quantum information science. In addition to that list of impressive highlights, Dr. Garcia-Severez played an early role in SURF's science program by serving as chair of SURF's Readiness Review Committee that evaluated the Majorana demonstrator project as that experiment prepared for installation at the Davis campus in 2012. Thanks to Dr. Garcia-Severez then and now, as we get ready to hear about the end of ionization.
Thank you, Garrett, for that very nice introduction. Let me jump right into it. Okay, so here we go. There's nothing wrong with your screen. This is my first slide. You probably maybe don't see anything. So that's because this is a talk about being able to actually see signals which normal methods cannot see. And so that's maybe a little better for the title slide, which I will skip over. And so traditionally, we in particle physics have always seen particles through their ionization of materials. And what I mean by ionization in this talk is very general. So it's not just producing, taking an atom and ionizing a single atom, but generation of mobile electric charge in an otherwise neutral medium. So when a semiconductor detector, which is, as you heard, something I also work on, when you promote charge carriers across the band gap, I am calling that also ionization. And of course, in gases and liquids, as in LZ, there is ionization. And then in metals that detect photons, there is a photoelectric effect. I also call that ionization. So the phototubes, for example, work in the same way. That's how photons are detected. However, there's more physics below ionization threshold. And so the nice thing about ionization that we've always used to detect particles is that it hides all these other processes because, of course, particles are very rare. It's amazing that you can detect one relativistic particle in kilograms of material, and that's because it ionizes. And there's a whole bunch of stuff going on in kilograms of material, but all that stuff is below ionization threshold. So as soon as something ionizes, all that other stuff is hidden. And so there's, kinetic theory, statistical mechanics, chemistry, etc. All that stuff is invisible when you just look at ionization. And so what I like to say is that ionization is the divided line between particle physics and material science. And so with that in mind, we can go to the look at the search for dark matter that's ongoing worldwide. And this is a plot from the SNOWMASS report showing kind of the dark matter particle dark matter landscape. And of course, you're all very familiar with LZ, which is in this plot what's called operating. It's basically LZ. And of course, the black line is from 2021. So now it's better, as you know. But still, there's the operating detectors, there's planning detectors like future larger xenon detectors, And then there's a neutrino fog that you will know. And then there's this thing called new technology over here. And it actually, if you try to say where do things ionize, and there's a weird kink here because of interaction with electron recoil as opposed to nuclear recoil. But basically, this is everything that's operating, planning, and so on is where there's ionization. And the new technology lives in the part where there's no ionization. So my first dark slide is here. And that's what this talk is about. So with that, let me give you an outline of my talk. There are particle interactions that are too weak to ionize that we're actually interested in. And so I'll talk about sevens, coherent elastic neutrino nuclear scattering, and of course low mass dark matter, which is my main interest in this area. And so detection. And then I'll talk about how do we carry out detection without ionization, and that's using quasiparticles. What makes quasiparticles, which is, of course, hopefully dark matter if it exists, but definitely sevens makes quasiparticles. And then also what are the backgrounds? So what else makes quasiparticles? Okay, so this starting with coherent elastic neutrino nuclear scattering, which is something that we know exists. It's there. It's not some mystery. It's a very well-known process. It's been observed already. And it is the thing that causes this neutrino fog background that the xenon experiments are going to hit in the not too distant future. And then there's a nice plot. I have the references below. There's a nice plot showing the different contributions of different neutrinos from atmospheric neutrinos or solar neutrinos to this neutrino fog. And then you can see that this is a process that depends on the nuclear atomic number of materials because it's a coherent process. So it goes like the number of neutrons in a nucleus squared. So you have heavy, heavy elements like lead have a much higher cross section for this coherent process. And unfortunately, xenon is a pretty heavy element. It's right here in orange. And so it is quite sensitive to coherent neutrino nucleus elastics. But the interesting thing on this, I have my screen here. I don't know if I will. The interesting thing on this plot on the very right here is that while other processes have a threshold, the coherent elastic scattering doesn't have any threshold. So you can get energy transfers to a nucleus that go all the way down to zero. And that's very important. And so again, I can draw a line separating the same line as before, separating ionization from non-ionization. So coherent elastic neutrino scattering can still produce ionization. You can displace a nucleus enough as to rattle it enough as to cause it to lose electrons or ionize in a semiconductor. But if you don't, eventually the amount of energy as the process doesn't have a threshold, it goes all the way down to zero. The amount of energy imparted to a nucleus is too low to ionize anything, even semiconductors. But as you see, the cross-section goes up. This is for argon, because that's a paper here that nicely shows this. There is most of the events in coherent elastic neutrinos are way down here where there is no ionization. And if you have a detector that depends on ionization, you can just see this very high tail of the coherent elastic neutrinos. Okay, but my main interesting is not that, which is a known process, but it's dark matter, which maybe is there, maybe isn't. Oh, sorry, what happened? I'm very sorry. I just stopped sharing. I pushed the wrong button. Now I have to start sharing. Like my school. Okay. All right. Sorry about that. So I think I'm back. If I'm not, someone should let me know, but I think I'm back. So the dark matter, which is what I'm interested in at lower masses. So of course, at surf, you have LZ looking for dark matter, but generally in masses significantly larger than the proton mass. But there's a lot of interest and theoretical motivation for dark matter models, which are called hidden dark matter models in general, which produce particles that are lower than the proton mass. And so these particles can again produce cannot cause a whole nucleus to recoil or even an electron to recoil, but they just coherently interact with materials, and I'll get to that in a minute, and they don't ionize. So how do we deal with things that do not ionize? And we need a different method to detect them. And so that's what I'm trying to convey here, is that let's start with a semiconductor, because there's a very good analogy here. So in a semiconductor detector, you have a valence band, band gap, and conduction band. The band gap for silicon is not 3.7 eV, but because it's an indirect semiconductor, you actually need that much energy to promote a carrier across the band gap, because not only do you have to overcome the energy of the band gap, you also have to match momentum. And so if you have less than 3.7 eV of energy imparted into the material, you will not ionize, you will not promote any carriers across the band gap. And so we now are talking about signal. So this is old signal that has more than 3.7 eV. New signal is much smaller than 3.7 eV, so maybe even milli eV. And so of course you need something with a tiny band gap, let's say, and there is such a thing, which I'm calling band gap impedances here. When we have superconductors like aluminum, if you cool it enough, it's a superconductor. And the reason the superconductor is because the charge carriers pair up into Cooper pairs. And then there's essentially zero resistance. But those Cooper pairs have an amount of, you can break them. You can separate the charge carriers out of Cooper pairs by hitting a Cooper pair with a certain amount of energy. And that energy to break Cooper pairs is 0.36 milli eV for aluminum. So that's an interesting factor of 10 to the 4. So this is an effective band gap, because you basically have a process where you can absorb some energy and cause a change in a material, which is kind of let's call it in this talk equivalent to a band gap. However, when even in silicon, yes, at room temperature, you have a leakage current, you have thermal charge carriers going into the conduction band all the time. And so typically, if you cool silicon, then you suppress that, and you don't have that because you have a lower thermal energy. We have to do the same here. So if you now are talking about a 0.36 milli eV effective band gap, of course, that will be completely ruined by thermal energy. That's why you don't have a superconductor at room temperature in the case of aluminum. You have to go very cold to get aluminum to superconduct. And that's why. It's because if you're warmer, you just break all the Cooper pairs instantly. So we need to go down to something like 30 milli-K temperature for the detectors we want. Again, this is a factor of 10 to the 4, because you're reducing KT by 10 to the 4. You're reducing your band gap by 10 to the 4. So that all squares. However, in the case of electric charge carriers, we now have an electric current. We know how to amplify that. We know how to collect that. We put that into a circuit. So ionization already gives you very nicely electric signals, which is what we deal with in detectors, is electric signals. Breaking Cooper pairs does not give you an electric signal. So we need to develop methods for detecting these processes, which basically, how do you turn breaking Cooper pairs into an electric signal that then you can process in a circuit? So there's a lot of R&D currently, and this is what this quantized program that was mentioned before, a lot of that is aimed at this question: how do you turn quasi-particles into an electrical measurable signal. Another important point that I wanted to make is that this is a bit of serendipity. You're not in business at these temperatures if you don't have a dilution fridge. And dilution fridges used to be kind of odd things, specialty items that were very expensive and finicky and hard to use. But today they are commodity items that you can just buy off the shelf. And this is driven by the quantum computing industry. Luckily for us, we're not doing quantum computing, but we need to get dilution fridges. And so this is the worldwide production of dilution fridges projected out. And it's completely dominated, as you can see, by quantum computing. All other customers are smaller. And of course, our experiments are one of these other customers. And then there's, thanks to this, there's a lot of manufacturers of dilution fridges that turnkey systems that you can just buy that are coming online. And every year there's more. And there's a list here, which is a partial list. Okay, so now how do you turn quasi-particles into electrical signals? So here, you consider that there are a huge variety of ionization detector techniques in use. Often they contain gain, for example, multiplication in gas, as is used in LZ. Now, quasi-particle readout methods, on the other hand, there is already quite a variety, but not at the same level as our ionization detectors, which have been in use for more than 100 years. But we're also developing and inventing, adapting old methods, developing and inventing new ones. And I will focus on one method, which is quasi-particle trapping assisted transition edge sensors. That's the technology that we're using, and that's what's used in the Tesseract experiment. This is the Tesseract logo up here. Okay, so what is a transition edge sensor? So this, and then how do you read it out? And so this slide is one slide to a primer of that. So a transition edge sensor is just a little chunk of superconductor, which is biased. In other words, it's in a very cold environment where the material is superconducting, but then you heat the material by running a current through it, and you heat it just enough to keep it at the superconducting transition temperature. So that's hard to do because a superconducting transition is very sharp. But there's a method called you can actually achieve that with negative feedback, just like in an amplifier where you have an op amp with negative feedback, same kind of thing. You can hold with electrothermal feedback, you can hold your TES at the transition, and then when you have a photon, in this case, hits material, it gets absorbed, raises the temperature, and then that moves you in this transition curve, which is very short, but you get a little pulse. And then how do you read that out? Well, you have the workhorse of reading out these very cold transition sensors is squid amplifiers. Squids are not a new technology. They've been around for a very long time, but they're basically extremely sensitive magnetometers for this purpose. And you essentially have a current that runs through the squid by having a voltage bias and a parallel resistor. Basically, every time the resistance of the TES changes, the current changes in this inductor. When the current changes in this inductor, you have a magnetic field on the squid loop, and then the squid, a very tiny change of magnetic field at the quantum limited, in fact, produces voltage output that then you can send to an amplifier. And so that's how we turn quasi-particles, which are the things. So basically in this picture, there's no quasi-particles here. They're all Cooper pairs that are unbroken, and all the Cooper pairs are broken here. And in the middle, you have some broken, some not broken. So your quasi-particles, which are the broken Cooper pairs, are being turned into an electrical signal this way. And this is an example of a IR photon detector, which works exactly like this. It's a little TS with squid readout. Photon comes in. This is a kind of world record energy resolution currently, but you can see you can detect 0, 1, 2, 3 photons of these are IR photons, so telecom 1.5 micron wavelength photons, and very nicely resolved and detected. Now, in our case, we don't want photons. We want quasi-particles produced by dark matter interactions in some material, and so it's a little more complicated. So this in this example, the material is a crystal, some crystalline material like silicon, alumina, or sapphire or gallium arsenide. And there's some dark matter interaction, but it does not ionize. It cannot it doesn't have enough energy to do anything in this material that produces a free electric charge. So nevertheless, what happens is that you get some phonons, some energy in the material is just propagates as phonons, which have a down convert, but then there's some long-lived phonons in particular materials, and they can bounce around in the material. Now you can these phonons generally will bounce around. They have nowhere else to go. But if you put some aluminum, let's say superconducting aluminum, on the surface of the material, now you have a match of the phonon energy and the Cooper pair breaking energy. And so these phonons can actually break Cooper pairs in the aluminum. And so now you have your quasi-particles, which are your broken Cooper pairs, and you want to measure them. However, if you go back to this slide and you say, well, let's just put a TS, an aluminum TS on the surface, that's great. But this TS actually is very small. That's how you get good this energy. For this energy resolution, this TS is 8 by 8 microns. So if you're trying to cover the surface of a macroscopic thing with one 8 by 8 microns device, you will never absorb any phonons in it. So you need a lot of, much larger amount of material to absorb the phonons. And that's some big chunk of aluminum. But of course, that big chunk of aluminum will not have a good energy resolution if you use the TS, because it's big, it has a large heat capacity. And so you want a small TS. And so in this case, there's a tungsten TS, tungsten because it has a lower superconducting transition temperature than aluminum. And I'll tell you why in a second. And then a bigger chunk of aluminum to where it is superconducting. It's not a transition, it's completely superconducting. And so it only has Cooper pairs, but then you break them with phonons, and then those are going to be collected in the TS, and I'm going to tell you how. And this is an SEM, scanning electron micrograph of this kind of device, which really shows you there's a lot more aluminum than tungsten. This is a little tungsten film, and then this is just a little corner of the aluminum here. In this case, the tungsten is below the aluminum. In the picture, the tungsten is above the aluminum. It doesn't really matter. This is a device, a wafer covered with these little dots on it. You see are these things. Okay, so what happens? So then the Cooper pairs that are broken have a certain Cooper pair breaking energy, and they have a lifetime in the aluminum. They diffuse around. If they come to this overlap region of the aluminum, there's a lower Cooper pair energy in that material, that interface material. And then in the tungsten, there's an even lower Cooper pair breaking energy. So what happens is when by diffusion, some of these quasi-particles reach this interface, they down convert, they produce multiple quasi-particles in this device. And then the same thing happens here. Then because they down converted, they can't get back out because now they have lower energy than this energy. So this essentially captures. That's why it's called quasi-particle as trapping assisted, because this traps these quasi-particles in this material. And the point is that the original material, the crystal, was grams of material. You have a few phonons in grams of material, but now you have micrograms of aluminum that the phonons break Cooper pairs into. And then you have nanograms of material that you're going to heat up. So eventually, this is not a thermal detector. This thing has not thermalized yet. The temperature has not equilibrated. This little thing is the only thing that was become a little bit hotter, because once the quasi-particles get in there, they can't get out and they thermalize and they raise the temperature. That's your TS. So this is a very nice method. Of course, there's efficiencies all along here. And so this is the key to these detectors, is making it so that you have enough detection efficiency that you can eventually get your energy resolution for the phonon interaction in this material. And so there's even more complicated signal collection methods. And in this signal collection method, I'm using, there's a vat of superfluid helium. Now, this is something you guys can relate to, because there's, instead of liquid xenon, which is a liquid noble gas, we have used liquid helium, which is a liquid noble gas, and your interaction happens there. But instead of collecting charge carriers, as you do in a regular TPC, now you have phonons and protons, and they don't drift like in a regular TPC, they just bounce around. But when they hit the surface, they can actually evaporate a helium atom because there's vacuum above. And this is called quantum evaporation because basically instead of boiling the bulk, you just have enough energy imparted to a single atom to make it free of the surface. And that's a very small amount of energy in superfluid helium. It's about 1 millielectron volt is enough to evaporate an atom. And so you can get a 1 MeV phonon, evaporate one atom, but then when that atom just travels and hits a surface, which in this case is what I showed you before, a crystal, the adhesion of the atom to the surface because of van der Waals forces can release more energy than it took to deposit to evaporate the atom. So this is a gain mechanism. And then you get a gain of 10 or even 20. And then you detect the phonons that were produced by this collision of this atom with this crystal. And this is an actual experiment. There's a reference showing this quantum evaporation signal. In this case, we used a radioactive source, so we got light out. So we got photons, but that's to give us a trigger. And then after the trigger, sometime later, you get the quantum evaporation signal. And it's very clear. Okay, so I talked about how to detect quasi-particles, but where do they come from? So hopefully they come from dark matter interactions. That's what I'm trying to look for. Of course, this is the second source they come from, but I'm going to tell it to you first because that's the one I'm interested in. And so again, as a particle physics, we kind of view the world like this. There's a bunch of atoms floating around. There's particles that come in and hit atoms or nuclei or quarks or whatever, and then release charge, and then we measure the charge. In this case, we don't have that anymore. So we need to switch over more to a material scientist's view of the world, which basically there's materials which are collections of atoms and lattices and so on, with all sorts of modes that are not what we're used to as ionization. And there's excitations, which again are not ionization, which can affect those modes and produce, for example, phonons or quasiparticles. And the lattice can reorganize and so on. So this is why when we give up on ionization, we really also have to become a bit of material scientists. And so one of the consequences of that is that in the case of ionizing radiation, where we just care about one atom or one nucleus, it doesn't really matter what the rest of the material is to the interaction itself, to the dark matter interaction. The dark matter interaction is just looking at the nucleus. And so you are free to pick the best material to collect the charge, to isolate backgrounds, and so on. And as you well know, in the case of the WIMP dark matter search, liquid xenon won. It is the best material to search for WIMP dark matter. And that's because the interaction itself doesn't really care what the material is. It's just the detector itself that cares. And so there is one ideal detector, which is liquid xenon. That is not the case for the low mass regime. In the low mass regime, the dark matter is no longer going to interact with a single nucleus or a single electron. It's going to interact with the material, with the lattice, with the whole lattice. So the wavelength of the dark matter is longer than the lattice spacing. And the lattice properties actually matter to the interaction. And so there will never be a single material that will win the race for low mass dark matter. And so this is an example of a theoretical work showing, in this case, the sensitivity of different crystals to dark matter interactions. And you can see there's a range of sensitivities depending just on the material. It is the same dark matter interaction. And this is another paper showing that in some materials, you can even have directionality. So the interaction can be different depending on which direction you hit the lattice from. And so this is, of course, directionality is a very interesting property for dark matter searches. And so let me, I'm getting to the end, but let me now talk about how do quasi-particles, how do we measure quasi-particles without the dark matter interaction. So where do they come from if there isn't a dark matter interaction? Unfortunately, there's lots of quasi-particles in materials naturally, meaning, also dark matter is natural, but okay, this is even more naturally. So think again of semiconductors. So semiconductors have a leakage current, which we normally call dark counts. So like if you have a CCD or an SIPM, it has dark counts. And that's because there's leakage current. This is not the same as noise. Noise is your amplifier, white noise, and so on. But dark current is different. And so, for example, you have impurities or defects in semiconductors that greatly increase the leakage current. This is something that's affected by how you prepare the material, what you put on it, etc., how you treat the surfaces. So it's not so surprising that quasi-particle detectors also have dark backgrounds, so also have dark counts. In quasi-particle detectors, these dark counts are known as low energy excess, LE. It's interesting historically that the LE was kind of discovered, let's say, by people trying to use these detectors, pioneering the use of these detectors as an unexpected background. However, it should really not have been unexpected because it's actually the analog of dark current in semiconductors. There's even an excess workshop series that is devoted to this topic. It's all experiments that are dealing with quasi-particle C, low energy excess. And the level of low energy excess is linked to defects, imperfections, stress in materials, etc., just as leakage current in semiconductors is related to how you treat the material and how many defects it has. So this is a demonstration that we published some years ago. Actually, it only got into Nature last year, but it's a very nice measurement showing the effect of stress on this quasi-particle backgrounds on this LEE. So what you see in the picture here is two instances of the same sensor. It's the same design. It's just a 1 centimeter square of silicon with these quasi-particle assisted trapping TS detectors on it, the little dots. Each of the little dots is an aluminum island. The TS is too small to see, but inside each aluminum island, there's a TS. And one of them is glued, this one is glued to a chunk of copper, which of course is how you cool it. This has to go to 30 millikelvin or something. And then the other one is suspended by hanging it from wire bonds, which is a pretty crazy thing to do, but that's what's done here. So it's just hanging there from these wire bonds. And there's one gold wire bond that links thermally this to this, so that you can actually cool this also to 30 millikelvin. All the heat is going to go through this little single gold wire bond. Gold is a very good heat conductor at low temperature. And so what you see here is the measurements on this quasi-particle assisted TS. It's just the amount of signal as a function of the energy that's measured. This is the measured energy. There's no calibration source here. This is just dark counts. But of course, in dark counts, you have a spectrum. This is the spectrum of dark counts. Never mind this high part at the high end. This is essentially saturation, and this is maybe there were some cosmic ray events or some external background hitting the detector here. But at the low end, this is just dark counts. And you can see that they're very different. So by orders of magnitude. So the one that's glued has orders of magnitude more dark counts than the one that's hanging from wire bond. And this is because there is a CT, coefficient of thermal expansion mismatch between the copper, gold-plated copper here, and the aluminum and the silicon, and that causes stress. And stress essentially relaxes with time, and every time there's a relaxation event, some atoms rearrange themselves, let's say at the interface, that releases phonons that make quasi-particles, etc. So this is even something as simple as stress in the material causes a huge background to these quasi-particle detectors. Of course, no material is a perfect crystal lattice without imperfections, etc. And so you can see that this is very hard to get rid of. So here, of course, there's still stress because you have a aluminum film on a silicon crystal. Again, there's a CT mismatch there. There's going to be stress here. That's what this remaining blue is. The removing this glue stress doesn't get rid of anything going on at the sensor, and this is it. So now in a more recent paper, we are trying to figure out how to discriminate these events. And in this case, now you have a sensor with two channels, same kind of sensor, but now you see two little lines of detectors, so of aluminum TS, quasi-particle assisted TSs. And so they're two separate channels, and you can plot the energy in one channel versus the energy in another channel, and you can see very clear backgrounds. This is this dark counts, very clear dark counts singles. So this channel only, this channel fires, this one doesn't. Same here, this channel fires, this one, oops. One channel fires, the other one doesn't. There's lots of singles. There's also some again, this saturation here, but then there's also some coincident signals from the bulk itself, because there's still some low energy excess here, but most of it is in these singles. And so you could discriminate the ones that are coming from the detectors by simply having multiple channels and requiring coincidence, just like you discriminate dark counts in follow tubes on SIPMs, right? You require coincidence. So this works for quasi-particle assisted detectors. Here's a nice photon calibration signal showing for these are UV photons, 3D, showing again 0, 1, 2, 3 peak of photons hitting this green space. Okay, so now I think I've convinced you, hopefully, that we know how to detect signals that do not ionize. Still the field is still evolving, but we have a starting point. And so we have now an experiment called Tesseract, which is going to do dark matter searches with these detectors that I just showed you, these same kind of detectors. And so the ultimate underground site being developed for Tesseract is at Modan in France. They will run two fridges in parallels with this hourglass cryostat design to really get to some very low level of external backgrounds, one event per kilogram per day per kV. That's called DRU. And this is a Dark Matter New Initiatives project, and there's a CDR, Conceptual Design Report, in preparation for a DOE review this summer. And the runs on Modan, this is all, construction is going to start soon. The runs on Modan will be ready to go in 2029. Now, that 2029 is pretty far away, and we're impatient, so we would like to do something earlier. So we're also doing, in near term, we have a collaboration with Kamioka. There's a new cryo lab at Kamioka that was recently established. And here we have already installed a fridge. It's going to be a much more standard setup, just a fridge as you buy it with the shielding, just classic lead castle shielding. We're here aiming for less than 100 DRU, but that's okay for small runs. And so we have an agreement to do some Tesseract runs here, 2025, 26. So in conclusion, low mass particle dark matter searches probe a new regime below the threshold for producing mobile charge carriers and otherwise neutral media. Particles interact with materials rather than individual nuclei or atoms where their wavelength is, de Broglie wavelength of the particles is bigger than the atomic spacing. And then in this regime, quasi-particles take the place of electric charge carriers in our normal detectors that we've been using for 100 years. And the range of detectors, quasi-particle detectors, is still under development. But all of them have these quasi-particle backgrounds, which we can refer to as dark counts, which are really present in all materials that are known as LEE. Understanding, reducing, and discriminating LEE is needed by all experiments. And there's a lot of work going into this area. And Tesseract uses quasi-particle assisted trapping as well as helium quantum evaporation. And we will have runs in Kamioka in the near future, and then Modan in the a little bit less near future. Thank you very much.
Great. Thanks, Dr. Garcia Cerveris. That was a great talk. We have time for some questions.
Let's see if there's the questions. I need to see my screen. Maybe I can stop sharing for a minute.
Okay. I see Kate has a raised hand. Can we unmute Kate so she can ask her question?
Hi, Marisa. Thanks very much. That was really very nice, clear talk. I think it was on slide 20. I had a question about the directional sensitivity. Is that is it a directional sensitivity or a directional signal?
Yeah.
I mean, is
So in
it
this
something where
case,
you have
yeah,
a,
in this case, it's simply a modulation of the amount of the the interaction with direction. So
okay,
if the dark matter incidence direction is aligned with a particular lattice direction, each interaction produces a larger signal than if it's
I see.
aligned with the other direction.
So it's a rate. Is it a rate
Yeah,
or an
well,
amplitude as a function of
or
direction?
pulse height, you could call it. I mean, if you're just talking about single blips, then the pulse height is a pulse height. So if you had
Uh-huh.
enough statistics to have like if you have this plot here, for example.
So it is actually kind of a directional signal that you
That's a
could,
direction. So in this plot, you can see you're talking about. Here are the single
I actually can't see the
photon.
screen now.
Oh, you can't see the screen. Oh,
Yeah, I just see you.
how about now?
Yes, now I see it. Yep.
Okay. So in this plot here where you have a detector, so imagine dark matter comes in. So if this was a directional detector, then you would see, these are photons of a particular energy. But in the case of dark matter, which is a distribution, you would see a distribution here where the green square maybe from one direction, and then from the other direction it would be higher up.
I see. Is it also a cross section? I mean, is the interaction more likely in certain directions, or is it just that the amplitude would be higher if it's from certain directions?
That's a good question. I don't believe the cross section is different. I think it's really that the energy transfer is what changes.
I see. Okay.
But
Cool.
I'd have to get back to you.
Okay, thanks.
Good question. Others? If not, let me jump in with my question here. Toward the end of your talk, you mentioned underground, plans to move underground in France at Modane and also in Japan, Kamioka. Can you just say a few words about the benefit that quantum computers or quantum sensors, in your case, gain from being underground?
Yeah, so it's not the sensors themselves, right? But we're still doing basically dark matter target material where where we want dark matter interactions that we know suppress all other interactions. And even though our energy energies we care about are in the sub EV or regime, or like a cosmic ray interaction would produce KeVs of energy. So in principle, you could discriminate it that way. There's still radioactive backgrounds are still a big problem, and cosmic rays are still a big problem. The amount of energy that we're sensitive to is so infinitesimal that cosmic ray interactions in the cryostat or material or in the fridge material can actually produce low energy excitations that reach our detectors. And so for example, IR photons or just scintillation of materials, but also just simply heat, IR photons can actually cause backgrounds. And so we do have simulations that for background levels in our detector targets, and it is hard to simulate these lower energy processes, but there is some ways to do it, and we see our simulations show us that you're kind of dead on the surface and from cosmic rays, and you have to go on the ground, and then you have all the usual radioactive backgrounds from materials. So you have the purity of materials matters, and you want to remove radon and all the usual things that you want to do. The biggest background let's say signal mimicking processes are neutrons in our case. So neutron backgrounds where a neutron just scatters at a very small angle with in our material can produce backgrounds, and some of those scatterings again can be not on the target itself, but on the walls or something like that. and eventually give us backgrounds.
Maybe just a quick follow-up. Which target would go in first at Modan, and which targets might you consider for the Kamioka cryo lab?
So at Kamioka, we're setting up currently for helium because we're basically building a helium cell in Berkeley that we hope we'll be able to send to Kamioka. But the targets are really kind of small and quick to make. So the real all the time-consuming work goes into the shielding and the readout and everything, and the targets themselves are pretty quick. So that's easy to change and to do and to even do a variety. In fact, at Kamioka, we don't anticipating running anything for more than like a week or two at a time, just because of the size of the detectors and the backgrounds that we'll have. The year-long runs will only happen at Monan. But I have no idea which one will go first at Monan because it's way too far away in the future.
I do have a question here from chat that I can pass along. Slightly more general, how has the collaboration between material science and particle physics influenced the development of some of these new detectors?
There's been a lot of collaboration in the theory part between material science and particle physics, and that's the main area where we need to understand how these things are collected. So if you look at the author list here, right? So we have material scientists, particle physicists, material scientists, particle physicists, and so on. So these calculations, for example, of the interaction of dark matter with a crystal lattice, are calculations and how phonons downconvert and how phonons reflect and so on and how they propagate. These are all calculations that material scientists do for a living, and they have density functional theory codes that they run on high performance computing, and they can do all this stuff routinely. And it's not something particle physics are used to doing. So that's been so far the most obvious place where there's really, hand-in-hand collaboration, and all these papers have density functional theory calculations and so on that material scientists are doing. In the devices themselves, I think there's of course the superconducting device knowledge, and how do you build thin films, superconducting films? How do you get pure films? How do you measure, for example, phonon and quasi-particle populations and these kind of things, which their material scientists have been developing methods for a long time. So that is more in the engineering, let's say, and the fabrication aspect. Does that answer the question?
Yeah. On this slide, looks like about 24 materials listed there. And you mentioned there's no one best material. Are there more? Are there many more in the community, or that are being?
Yeah. So there's more materials. Yeah. This is a constant. This is, of course, from a while back. This paper, it's from 3 years ago. But there is a material science. Another reason to partner with material scientists. There are databases of materials that material scientists have developed. So, and then with properties and so on. So this is basically scanning some database and doing some calculations, automating some calculations on a database of material. But these are very simple materials, let's say, which we're all familiar with. People develop, much more complex materials these days. The problem is that they only make them in tiny amounts. But eventually, some of these more complex materials might prove more useful for a particular model, for a particular purpose, like, for example, directionality. Again, this is a polar crystal. This is sapphire. It's a natural material, but but there could be some two-dimensional material stack that would be a lot better for this, for example. So so yeah, and then there's also the materials have symmetries. There's topological insulators, things like that people are looking at for, again, for guiding phonons, guiding quasi-particles, or collecting them in different ways. There's interfaces. Can you make anti-reflective coatings for quasi-particles, for phonons, and absorptive coatings, and by having layered materials? All these things are being investigated. So this is just scratching the surface.
Yeah, no, very exciting times. Well, I think we have to wrap things up. Thank you, Dr. Garcia-Severas, again for lending us your expertise for the Deeper Talks seminar series. It was great.
Thank you very much.
To the audience, just a quick reminder that this talk will be available to view and share using the same link you received to join this webinar. And you'll also be able to find it on the Sanford Lab Vimeo channel and the Institute.surf Deeper Talks website. Quick intro or promo for next month's Deeper Talks. That'll be held February 12th, same time, 9 a.m. Mountain. We'll stick with the quantum theme with Dr. Oliver Buckmuller from CERN. And the title of his talk will be Exploring the Universe with Quantum Technology, the New Frontier in Physics. Before you leave the webinar, there'll be a short survey included in the event lobby after the event is over, and also emailed following the event. We appreciate any feedback on this event and any suggestions for future talks and speakers. And with that, we will wrap things up. Thank you very much for attending, and let's hope to see you at the next event in February. Thank you again.